Hi, I'm Casey Klarman, and this is my Physics 2211 Lab 3 on the black hole. Introduction. The purpose of this lab is to analyze the orbit of the star around a black hole to find the mass of the black hole, then use this information, the mass of the black hole, to determine the initial velocity necessary to escape the black hole without crashing into the planet or the event horizon. Our fundamental principles are Newton's second law and Newton's universal law of gravitation, and the results of this lab was we found the mass of the black hole to be 1.16 times 10 to the 34th power kilograms, and the initial velocity of the ship to be -6 times 10 to the 7th meters per second in the x direction, and 2 times 10 to the 6th meters per second in the y direction. Our fundamental principle shows that F net is equal to the change in momentum over the change in time, and that F net has a perpendicular and a parallel component. The perpendicular component is the change of direction of the ship and the force, or of the system, and it points in the n hat direction, perpendicular to motion. And the parallel component is the change in momentum, or the change in speed of the system, and it points in the p hat direction, either positive or negative. The law of gravitation is the equation shown here, and the magnitude of it just doesn't have the r hat vector. And for this experiment, we're assuming that the F net is equal to the force of gravity, and that means that we can find the equation to be the mass of our black hole is going to be equal to the change in momentum over the change in time times the position vector squared, or times the magnitude of position squared, all this divided by the gravitational constant and the mass of our star. Reasoning. F net parallels the same direction of motion, then the object speed is increasing. If the for F net in the perpendicular direction, it changes the direction of the object, and its components point towards the center of the kissing circle path, so the n hat direction. The only force acting on the star is the gravitational force of the black hole. The forces acting on the spaceship are the gravitational force of the black hole and the gravitational force of the planet. Importantly, the universal gravitation is not a constant force, so average velocity will be replaced with final velocity in the model. Here's our initial conditions, as shown in the code to our right. The system is the black hole, the surroundings is the star, and the black hole is initially at rest. The mass of the star is 2 times 10 to the 30th power kilograms, and the time step for our model is 1 day. Here's our code details. In the blue, we have F net, so Newton's second law being F net equals change in position over change in time, as we did here, where we have our delta P over delta T. Our parallel component, we found the P hat. Then we did the derivative of the magnitude of position over the change in time, which is the change in the magnitude of position over the change in time. And we multiplied that by P hat to find our dPdt in the parallel direction. And then we found our F net parallel to be the dPdt in the parallel direction. Same thing for the perpendicular, where we just subtracted, where the difference of the change in position over change in time is going to be equal to, the change in position over change in time in the parallel direction plus the change in position over change in time in the perpendicular direction. So the change in momentum over change in time in the perpendicular direction is going to be equal to the change in momentum over change in time minus the change in momentum over change in time in the parallel direction. Here we have our equation for the mass of the black hole. We have our F net, the magnitude of F net, multiplied by the magnitude of position vector squared, all that divided by the gravitational constant times our mass of the star. We found our mass of the black hole to be 1.6 times 10 to the 34th power kilograms, and our F net being 8.61 times 10 to the 28th newtons, and the parallel component being 2.28 times 10 to the 28th newtons, and our perpendicular component being 8.32 times 10 to the 28th newtons. Here's our initial conditions for the second part of this equation, or second part of this experiment. The system is our spaceship, and then the surroundings are the planet and our black hole. And our black hole is at rest, and we can see the mass of our black hole is changed over, and the mass of our planet is 9 times 10 to the 20th power kilograms. And our time step is 1 second. Here we are going to find our r hat. In the blue, we have the r hat component and our r component. For the planet to the black hole, in our gold, we have the universal gravitation for the planet to the black hole, and these two is just the same thing but with the ship to the planet, and then our F net is going to be the sum of those two forces. And again, we do this, but instead of this system being the planet, the system is the ship, and we found the exact same thing where the F net is going to be the force of the black hole in the ship plus the force of the planet on the ship. Here we are simulating the movement, so we use the velocity update formula and the position update formula for the planet, and we do it again for the ship. Here is my experiment for the spaceship leaving the planet. We need to make sure that it does not collide with the planet. So I found the initial velocity necessary was -6 times 10 to the 7th meters per second in the x direction, and 2 times 10 to the 6th in the y direction. And the closest that the ship got to the black hole was 7.37 times 10 to the 7th meters away from the event horizon of the black hole. Here's our what if. If the spaceship were to, instead of just trying to get close, orbit the black hole, we would need the initial velocity to be similar to the planet, but a slightly smaller x component and slightly larger y component in order for it to escape the planet first. So we found that the initial velocity necessary was -3 times 10 to the 6th meters per second in the x direction, and 8.91 times 10 to the 6th meters per second in the y direction, which was just a little bit bigger than the initial velocity of the planet in the y direction. and our orbital velocity was 9.41 times 10 to the 6 meters per second. What does it all mean? The force of it is harder to find the F net than it is to just find the change in momentum. So that's why we decided to just find the change in momentum rather than doing a bunch of F net equations. So because F parallel is just the magnitude of force, over the change in magnitude of force over the change of time times the p hat component, it's just a lot easier. So we just did that.